We want to look at now special graphs, and these are ones where we have some multiplicity. So let's examine this one, x times x plus 1 to the power of 2. We know this function is degree 3 because you've got x times the x squared when we expand it out. So we possibly have 3 roots. We know that. So when we look at the roots of this equation, though, we see that if we write it in either way, we get roots of 0, minus 1, and minus 1. So because we've got 2 roots at minus 1, we say that's got a double root. That's a term we're going to use. It's got a double root there. If it was x cubed, there we'd have a triple root. So, or it was x power 4, we could triple root. So it could go on. We're not going to see too much of that. But sometimes we'll see double roots and triple roots. So if that's the case, basically when you get a double root at an equation, of an equation, the function there, as we said in the last video, will also turn at the x-axis. So it not only is a root, but it's also a stationary point. Now, we can prove it over here, because if we look at x outside of x plus 1 all squared and expand it out, we expand it, not expanding it, we're going to do the product rule on this. So, and we got the derivative of it. Set it equal to 0. When we factorize x plus 1 out, because it's common. But if you set it equal to 0, you can see you get a stationary point at x is equal to minus 1, and then you can solve for the other stationary point. But you've got a situation here when you've got the squared there, that you're going to get a root at that value of x is equal to minus 1. But because of the nature of it, the product rule and factorizing it out at the end to get, when you set it to find your stationary points, you're going to get a stationary point at that value as well. So you've got a root, but it's also a stationary point, and that's what happens when we get a double root there. So that's what we need to look at. So if we look, so graphing that one up, we can see that when x is equal to 0, we get the y-intercept, but also it's also going through the origin, because when y is equal to 0, x is equal to 0, and x is equal to minus 1. Because it's squared, we're getting the double root there, and then also we're getting the nature of the curve. As x approaches infinity, y approaches infinity, x approaches negative infinity, y would approach negative infinity. So if we have a look at x minus 1 all squared, well, we know that's a parabola, but also we know it's a parabola that's turning at minus 1, at positive 1, and also so it's a root there, but it also is a turning point. So we know that's what that looks like. So that just emphasizes our point on the double root. So minus x plus 3 all squared, well, again, we know we've got a stationary point at minus 3, so as well as it's a root there as well. So we can see it's concave down because it's a negative, and also that it's going to be turning at a stationary at the root there. So because it's a double root there. Again, x squared, x plus 1, well, it's got a double root there at the origin, because when x is equal to 0, y would be equal to 0, so it's going to go through the origin and have that double root at that point. The other root is minus 1, again, because it's x cubed, x approaches infinity, y would approach infinity, x approaches negative infinity, y would approach negative infinity. Again, here's our double root at x is equal to 2, so we can see the double root at 2, and it's also got another root at 0, and we've got our shape of the curve. So notice about roots of the equation, for multiple roots, they're touching the axis. So that's what we want to really pick up about those ones there. Now let's just have a look at these ones here and see if we can look at something that's and get some idea. Have a look at the degrees here and what's happening at the ends of each of these equations. So for degree 4, if we have a look and see what's happening there, degree 6, if we have a look there. Now hopefully we can start to make some insights about these, that when the functions, ends of the functions, when they have even degrees, will always approach positive infinity. So it doesn't matter whether it's x approaching positive or negative infinity, the ends of the functions will approach positive infinity, so they'll go up all the time. They'll keep going. So that happens on all even functions. So, well, functions with even degrees, sorry. When the functions start to have odd degrees, what do we start to notice? Well, we've seen our polynomials like that, degree 3 looking like that, degree 5. So this function here will go through -3, 0, 1, 2, and we have the double root at 0. And if it's at 7, so we've got x minus 2 all cubed, so that's actually going to have a horizontal point of inflection, double root at 1 and a double root at -3. But have a look at the ends of functions with odd powers, and hopefully we get the idea that they will start to approach the opposite directions. If you can see there, doesn't matter whether it's negative or positive, which way they go, they will always go in the opposite direction there. So it's what we're looking at when we're the degree of the leading term has an odd power.